Guys, in this lecture, I'm going to talk about the electrostatic properties of conductors. So this is the properties of conducting materials when all the charges are at rest. Okay, so in electromagnetism, we usually describe materials as being one of two types. And this is a bit of an oversimplification because there's a lot of materials that are somewhat in between these two types of idealized materials. But for our purposes, it's nice just to think about these two distinct types. Okay, the first type is called conductors. Okay, and conductors are special because the electrons in the atoms that make up conductors are free to flow from atom to atom. Okay, essentially they move easily through the materials in a solid. As the book points out, if we have a conducting liquid, it's actually ions that are moving through, so actual whole molecules or atoms. Okay, it's important to remember that the electrons, they move fast, really fast. Okay, in fact, they adjust almost instantaneously to electrical forces. Okay, the other type of materials that we can classify objects in is insulators. Okay, and insulators are basically on the other end of the spectrum from conductors. For insulators, charges, they don't move through the material. They are basically, electrons are basically bound to the atom, or more bound to the atom rather. They cannot easily flow from atom to atom, although charges can shift, okay, which is what we call polarization. So I could bring a charged object near an insulating object, and I could actually push, for example, the electrons further away from the surface of that insulator and create a little area of polarized charge. Okay. Another important fact is if you stick some excess charge on an insulator, it stays put. Okay, so an example of that, a balloon is a good insulator. If I rub a balloon against my hair, I'm actually taking some of the electrons from my hair and depositing them on the balloon, and those electrons are going to stay exactly where I deposit them on the balloon. They're not going to travel around the balloon and distribute themselves uniformly. Okay, so we're going to, in this chapter, focus in on conductors because they're a little bit more interesting to think of in terms of electrostatics. So the question is, what happens when you put excess charge, so extra charge, on a conductor? Okay, so I'm going to just draw a simple conductor here. Of course, I'm drawing it in 2 dimensions, but you can imagine this being a 3-dimensional object. Okay, if I put some excess positive charge on this conductor, that positive charge is going to move all the way out, okay, to the outer walls of the conductor. Okay, and in fact, if we know anything about atoms, right, it's not really the positive charge that's moving. What's going to happen is the electrons are going to move inward and leave an excess of positive charge in the outer walls. But for the case of understanding conductors, in this class, it's okay to think about positive charges moving, even though we know, in fact, that it's the electrons that are moving. Okay, so I know that the charges move to the outer wall of the conductor. Okay, so you might wonder why the charges move out to the outer wall instead of being, I don't know, distributed uniformly throughout the conductor far away from one another. Well, the easiest way for me to think about it is, right, these positive charges, again, it's easier to think about the positive charges just moving in this case, they're all repelling one another, and they're basically going to move until they reach some kind of static equilibrium. And when they're in static equilibrium, that means that all of the forces, let's focus in maybe on this charge right here, all of the forces on that charge are balanced. Okay, so if I look at the forces on this charge right here, well, I've got forces acting on it from all of these other charges, right? This charge is going to exert a force maybe to the right, and this charge over here will exert a force to the left. Okay, and then maybe some of these other forces are these other charges are going to exert a force again to the right and left, but a little bit up and of course shorter. And basically, the charges are reconfiguring until the only force left is a force that's actually pushing the charges up against the wall. Okay, which is to say, okay, maybe there is some magical configuration that these charges could all be inside of our conductor, where they would all be in equilibrium, all of the forces on all of the charges would be balanced. But it's much easier to imagine these charges just kind of scooching away from each other and then pressing themselves up against the wall until the forces on them are balanced. Okay, so this is an easier configuration to get to than one where they all just happen to get to exactly the right placement on the interior. Okay, spread against the wall and pushed against the wall. And they really are, in electrostatics, each in equilibrium, which means all of the forces on these are balanced. Of course, I'm showing an excess electrical force pushing this charge into the wall, but there's going to be a kind of a normal force pushing in the other direction. And by the way, I've drawn, because it's just kind of a limitation of drawing, I've drawn these positive charges kind of inside the wall a little bit, but you really want to think about the excess charge being on the surface, very much on the surface, and not at all in the interior of your conductor. Okay, so what is the result of this charge configuration? Well, the result is that the electric field has to be zero inside the conductor. Okay, how do I know that? Well, I can draw a Gaussian surface, and really I'm drawing this kind of interior to those charges, but I could draw it just on the inside of the wall of a real conductor. And inside this Gaussian surface, I know that the enclosed charge is zero because all the excess charge is on the wall. Okay, therefore I can conclude that inside my conductor, this electric field is also going to be equal to zero. Okay, and again, the charge is always going to move in order to make it so. So I know that the electric field is always, always, always going to be zero inside a conductor because the charge is going to reconfigure itself in order to assure that the electric field is zero inside my conductor. Okay, because the electric field is zero inside the conductor, I also know that the charge density, which is the excess charge per volume, is also zero inside the conductor, which is to say, not that there isn't any charge inside the conductor at all, but there's an equal number of positive and negative charges, so there isn't any charge imbalance inside the conductor. And I can get this also out of the math from the divergence theorem. which tells me that, right, that charge density is equal to the dot product of our del operator and the electric field. So of course, if this is 0, then our charge density also has to be 0. Okay. I also know, as a result of this charge moving, that the electric field is perpendicular to the surface of the conductor. Okay, if this wasn't the case, then the charge would move, okay? So I know this has to be true because any electric field parallel to the surface would cause the charge to move. Okay, and I know that it's not moving. That's what I said was true. The charge is going to move until it's in equilibrium. Each charge is in equilibrium, and it is stationary, static equilibrium. Okay, the last thing I want to note is that all of the conductor is at the same potential, okay? How do I know that? Well, again, if it wasn't at the same potential, if there was a gradient in potential, that would tell me that there was an electric field, right? The negative of the gradient is equal to the electric field, and charge would move in response to that electric field. And I know that's not happening, okay? And I can also use this equation here, which tells me the difference in the potential between 2 points A and B is equal to the negative of the line integral of the electric field dotted along that line. I know this has to be equal to 0 because E is equal to 0. Therefore, my potential at these 2 points has to be the same. Okay, but the main points here I want you guys to take away is for my conductor, okay, I know the electric field is 0 inside. I know the charge density, which is 0, which means there's an equal number of positive and negative charges inside. I know the electric field is perpendicular to the surface, and I know that all of the conductor is at the same potential. Okay, and then I do want to draw the electric field, so let me draw that quickly here on my conductor. Alrighty. And I'm just trying to draw it again, so these field lines are perpendicular to the surface. And if I was doing this really right, the density of the field lines would perfectly represent the strength of the electric field. I'm trying to do that a little bit, but it's not going to be perfect. All right, so there's my electric field. All right, let's borrow that picture and talk a little bit more about the properties of our conductor. I've tried to draw it so that here, even in this picture, the charges are accumulating in pointy or more curved bits. So by that, I mean the charge density, let me write that a little bit better. The surface charge density which is our sigma, is larger in pointy or more curved bits. Okay, and this is always a little bit of a complicated thing to explain, but I think the simplest way to think about it is to draw kind of a like a guitar picked shaped conductor. And I'm going to draw a couple of positive charges in here. And these two positive, let me draw those a little bit further in. Each set of these positive charges is going to be pushing away from one another, repulsing one another. These two positive charges, right, the force they're exerting on one another is going to look kind of like that. And these forces are, of course, going to cause these two charges to move away from each other, of course, until that force is balanced by maybe another positive charge above and below it. If I draw those two forces here for these two charges, notice that these forces, just because this is a curvier bit of the conductor, a lot of that repulsive force is just, instead of pushing these two charges away from each other, it's just pushing it up against the wall. So when I think about a lot of positive charges accumulating here, it's because that repulsive force of these charges is actually pushing the charges up against the wall harder rather than pushing them further away. So, okay, again, but the take-home message here is that if you've got a curvier part of your conductor, there's going to be a larger accumulation of charge on the surface there. Okay, so the way that the charge distributes on the outside of the conductor is dependent on the shape of the conductor. Okay, what happens if you put a conductor in an electric field? Okay, I'm just going to draw another conductor here, any shape I like. Okay, and this one I'm going to put this conductor in a rightward electric field. So I'm actually just going to draw a couple of electric field lines here, and I'll draw the rest later. Okay, notice the electric field lines I've drawn, they're still roughly perpendicular to the surface. If I put this conductor in this electric field, the charges are still going to move so that the electric field is zero inside my conductor. Okay, so what that means is they are going to produce, if I look inside this conductor, the external field would be pointing to the right. The charges are going to move in order to produce a kind of cancellation field or an electric field that would point to the left. There is going to be no electric field because the superposition of those two fields is going to give you zero, but the charges are going to move in some complicated way to produce an electric field that would cancel out this external electric field. So in this case, in order to produce what would be a rightward field, or a leftward field, sorry, inside the conductor, I get accumulation of positive charge here on the right side and accumulation of negative charge on the left side. Okay, this kind of charge configuration, and it wouldn't look exactly like this, it'd be more complicated, but even for a neutral conductor, the charges are going to separate, and in fact, what's going to happen is the electrons are going to move throughout the conductor and gather on this wall in order to exactly cancel out the electric field everywhere inside the conductor. Okay, when that happens, you are going to affect that external electric field near your conductor, and you're still going to get the property that the electric field is going to be perpendicular to the surface outside of the conductor. So maybe looking something like that, and something like that. Okay, and some field lines are just going to go around, but it's kind of like a pebble in a stream, except for our stream is going to directly intercept my conductor. Okay, but inside the electric field is zero, outside the electric field is going to be modified by the presence of the conductor. And the take-home message here is that the charges inside conductor, they redistribute to cancel the electric field inside the conductor. And again, they don't really have an agenda. They just initially sense that electric field that this conductor is placed in. When they sense the field, they move, they respond to it, and they basically move like they're rolling down a hill until they get to the bottom of the hill and they come to a stop. Okay, when they come to a stop, they've produced a charge configuration that happens to cancel out the external electric field. All right, the last little bit I want to talk about is what you can say about the charge and the electric field at the surface. So basically, how can you relate the electric field and your surface charge density at the surface of a conductor. Okay, so I'm going to just draw a little surface of the conductor here. Okay, and inside our conductor, we've got an electric field equal to 0, but maybe at the edge here, we've got some charge that has accumulated. Okay, I know that sigma, which is our surface charge density, it is not necessarily uniform. It can be for some shapes. We'll just say it depends on the shape. Okay, so just like I said before, if you've got pointier bits or curvier bits, you're going to get a larger charge accumulation. Okay, but even though I know it's not going to be uniform, sigma can still be related to the electric field just outside the conductor. Okay, so let's think about how we can do that, all right? So I'm going to draw a little Gaussian surface here. Okay, and this is related to the earlier lecture that we talked about boundary conditions during. Okay, but I'm going to draw a little Gaussian cylinder. So this is a little Gaussian cylinder. On this side of my Gaussian cylinder, I know that the electric field is 0, and I'm trying to figure out what the electric field is just on the other side of my Gaussian cylinder. So what is the electric field right here? And this is going to be a small epsilon. Okay, so I really want to think again, if I look back here, the electric field gets pretty complicated if I get far from the surface, because the electric field is going to have contributions from a bunch of little patches of the surface. I want to think about getting so close to the surface where I'm evaluating the field that the conductor is basically flat. Okay, so I'm getting really close to the surface of the conductor and figuring out what the field looks like there. All right, so if I use Gauss's law on this little Gaussian pillbox that I just drew, I know that the electric field along the surface there is going to be equal to the enclosed charge divided by epsilon naught. Okay, if this has an area of A, then the enclosed charge is going to be equal to sigma times A over epsilon naught. Okay, so this is my Q enclosed. Okay, and then the left-hand side, I'm going to get 0 times A for this side here. Okay, and then I'm going to get my outward, my perpendicular component of the outward electric field times A for this side here. Okay, and then 3 and 4 are just going to give me 0. Okay, because I know that there is no electric field parallel to my surface. Okay, so that's all going to be equal to sigma times A over epsilon naught. So I'm left with my electric field outside of my conductor in the perpendicular direction is equal to sigma times A over epsilon naught. I need an A here. The A's cancel out, and I get that my electric field again out is going to be equal to sigma over epsilon naught in the normal direction or perpendicular to the surface. And this looks like what we found before when we were talking about boundary conditions. Okay, and it's important to point out that this is just above or outside the conductor. Okay, which is to say, as I travel along the surface of the conductor, the electric field is always going to be perpendicular. The magnitude of it is going to vary as the charge density varies. Okay, And it can even, right, it's going to be outward or inward depending on the sign of sigma, okay, as I go along the surface. If I'm up here at a point here, and I want to figure out what the electric field magnitude and direction is, then I got to integrate the contribution from a bunch of patches of surface, just like I would for, I don't know, any other object, okay? So it doesn't stay constant and perpendicular as I go far from my conducting surface, of course, unless it is a straight plane where we figured out that this was the electric field everywhere for an infinitely long straight plane. Okay, let's think about our charge density. Okay, I said it was 0 inside, okay, because the electric field, that gives me that the charge density is equal to 0 inside the conductor. And I also know that rho is equal to 0 outside the conductor because there's no charge. Okay, so the only place where I can have a non-zero rho or charge density is at the boundary. So that means that our divergence of the electric field, which is equal to rho over epsilon naught, is very big at the boundary of a conductor.